you to my lecture today. Today I'm actually going to repeat what we did on Monday. You know why? Because on Monday I read the countenance of the students. I realized that your mind was on that assignment that you wanted to submit on Tuesday. So I realized that, most of the students were not that focusing. Okay. And that is why it's not your fault, because I have been student before. So I know some of you were battling with the assignment, and that's why I basically want to, start all over, start this topic all over again. Does that make sense? And that's why I'm presenting the slide that you see now is the one for Monday, and I'm going to start afresh. Okay, so I want to welcome everyone to my lecture. This is our core principal component analysis, or PCA. Okay, I'll be guided by the outline. I'm going to introduce you to PCA, then the procedure. Now, what is principal component analysis? Of course, the idea behind principal component analysis is when we are looking at a relationship, or maybe we're trying to predict a particular dependent variable from independent variables, and we got a lot of independent variables. Okay, and of course, in statistical analysis, it is a special requirement that if I want to look at the effect of so many variables on the dependent variable, there shouldn't be a multicollinearity. What do I mean by multicollinearity? Is that variables, the independent variables, shouldn't have relationship. They shouldn't depend. They should be truly independent. But let me tell you this. Situation where you got more than, where you got so many variables, so many independent variables, of course, that is basically going to be problematic to the model. And of course, there's going to be a higher chance of, getting multicollinearity. And, a model is as good as assumption put into a model before we can trust whatever that comes from our model. Assumption must not be violated. So what I'm trying to say now, if the assumptions underlying the use of a model is violated, like assumptions of there must not be a linear relationship among the explanatory variables. When I say explanatory variables, another name for that is independent variables. We also call them predictors. Relationships should not exist. So when relationship exists, of course, it could be damaging. And that is the reason why at times it's basically going to look as if our models are failing us. Our models are not failing us. We are the one that ignore assumption violation. Now, what are we going to do in a situation where the independent variables correlate? One of the intervention is what we call the principal component analysis. Now, let me tell you this. Let me say, broadly speaking, we got two ways. Okay, broadly speaking, we got two ways. We got what we call feature elimination, and we got what we call feature extraction. Okay, for instance, if I want to reduce dimensionally because in a situation whereby you got a lot of independent variables, okay, then your data will be of high dimension. You collected observations over so many variables. Your data will be of high dimension. And let me tell you, we need to reduce that high dimension into simpler dimension, because it is only when we're able to do that, okay, that we can guarantee, okay, or no any issue. Now, if I have so many variables, I'm going to give you an example now. Maybe I want to predict United States GDP. Okay, maybe I want to predict for 2023. Okay, if I want to predict United States GDP for 2023, of course I need a lot of information available. Information like, okay, US GDP for the first quarter of 2023. I also need US GDP for 2022, for 2021, and so on, like that. Not only that, I also need, employment, unemployment rate, unemployment rate, inflation rate. In fact, I also have information about consumer price index. What about information about stock price? Okay. What about maybe I also have information about maybe 2000, looking at 2010 census data. I know how many Americans that work in a particular industry. Not only that, maybe I also have information about the number of maybe senators or numbers of House of Representatives that belong to a particular political party. Now, there's a lot of information that's available. And looking at the informations that we have, if I basically want to go by way of feature elimination, then it means I'm going to look at them and eliminate some that we may believe that are not important. But let me tell you the danger of feature elimination. The moment you eliminate some variables, you're actually going to lose information about them. I'm going to say that again. The moment you discard, the moment you eliminate, okay, it means you cannot have information about that variable anymore. And that is the reason why we don't normally want to go with this. But with feature extraction, the principal component is a member of feature extraction. We actually, for instance, let's say we got 10 variables, 10 independent variables, and the 10 independent variables are actually correlating, which means there's a problem of multicollinearity. Now, what we're going to do, we're actually going to produce 10 new principal components in such a way that each new principal component can be expressed as a linear combination of all the old ones. I'm going to say that again. Let's say, for instance, we got 10 independent variables that are correlating. Okay. Of course, we cannot use them in our model. There's going to be a problem because they are correlating. Now, we're now going to produce 10, using feature extraction, we're going to produce 10 new principal components in such a way that each new variable as all the old variables, each of them as all the old variables. But at the end of the day, we're not going to use all the 10 new principal components. We're only going to use few of all the 10 new principal components. That I'm going to say that again. You got 10 independent variables. The old one, they are correlating. There's a problem. We created new set of, if I have 10 of that, I'm also going to produce 10, that same 10 principal components. And each principal component is a linear combination of all the old ones. So what I'm trying to say in essence is more or less like, if I actually have, let's say I have x1 up to x10, that is what I'm trying to say. If I have x1, x2 up to x10, but these are correlated, then I'm going to produce 10 new principal component. Maybe I call that W, which is going to be a linear combination. Like I'm going to have W1, W2 until I go to W10. And in each of that, I'm actually going to have this. So which means every new principal component will still retain the old variables. Okay, but in the end, we're not going to use all the 10 principal components. I'm actually going to walk you through a threshold, like what are we going to use to select just few of the new principal component. If I select W1 and W2, okay, so which means I've already eliminated W3 to 10, but in W1 and W2, I still have the whole variable information. Does that make sense? So that is the idea. Now, this is what I wanted to know with the principal component. The question is, when do we consider PCA? I'm going to say that again. When do we consider using principal component analysis? Number one reason is when you have a lot of variables, explanatory variables that are correlating, and you don't know the one to drop. You are faced with a problem because maybe looking at them, I want to predict US GDP for 2023. The US GDP for first quarter, of course, it should be relevant. The US GDP for 2022, 2021, and so on should be relevant. Employment rate, of course, should be relevant. You know, maybe I saw a lot of variables available, and I realized that they are looking relevant to me. I now face the problem, you know, of dropping anyone. Then I'm going to consider the PCA. Another reason why we need to consider PCA, if I actually have sets of, you know, independent variables that are correlating, then the PCA can convert them into uncorrelated variable. I'm going to say that again. PCA helps in converting, you know, variables that are correlated to the uncorrelated one. Don't forget, in your regression analysis, we need uncorrelated independent variable. We don't need a correlated one. So the PCA can do that job. Okay. Then number three, reason why we use PCA, okay, if we are comfortable, okay, with less interpretable, okay, less interpretable independent variables. Because let me tell you this, by the time we are using the principal component analysis, okay, then the new principal component that we have, okay, we lose certain interpretation because we are no longer working directly with the old ones. We're now working with a new set of variables. Does that make sense now, right? Okay, now I think I've justified to you, okay, why we need PCA. And of course, if you don't actually use data extraction, feature extraction, or feature elimination, of course, like I said, there's going to be problem, because when you have several independent variables that correlate, okay, what kind of problem is it going to cause? If we ignore that, it's basically going to cause problem of overfitting. Overfitting is a problem in statistics. Overfitting actually means your model will perform greatly with training data, with training sets, but your model will perform poorly with test data. Okay, but the model will perform poorly with test data, because at times in statistics and in machine learning, we split our data set. The training set is for validation, model validation. Okay, why the test, the training set is to build your model, which you call, model building. But the test set is for model validation. Imagine your model perform very well with your data, but the model perform poorly with unseen data. That's not good. And it is because of the problem of overfitting. So why do we have overfitting? Because there's a lot of variables in your model. There's a lot of variable in your model. Okay, and that's why we want to use the idea of PCA. Now I'm presenting, and what we always, this is another example. Got a lot of variables, and probably we actually want to see if that can be pruned down. Okay, this is a data set that consists of chest, waist, and height measurement of a sample of 20 men and women. I think on Monday I gave you another example that has to do with housing, housing data. We're looking for the possibility of trying to prune the numbers of variables we have into manageable size. Okay, there's so many. So the idea behind this is like, oh, when I have so many independent variables, then there's going to be issue, because some of them will be correlating. Okay, this is what we're going to do. It means if we really want to use the principal component analysis now, we need to be able to investigate that relationship among the independent variables. Because we said that when there's so many variables, there's possibility that the independent variables, they will have relationship. And how do we measure relationship in statistical analysis? To measure relationship we use correlation. Of course, you know the definition of correlation. The correlation actually measure the strength and the direction of the relationship between two variables or more. But how do I get to correlation? Oh my God, the correlation is a lot of like, I'm going maybe from here. I want to get to maybe my office. If the correlation is in my office, I know I will have to walk before I get to my office. If I want to get to correlation, then I will pass through variance. I will pass through covariance before I will get to correlation. Now, if I basically want to investigate now, I'm going to start investigating relationship. If I have so many variables, I can be looking at them two at a time. Okay, one is going to be called X. The other one is going to be called Y. Now, if I start with, I can look at variation within X. Variation within variable X is called variance of X that I'm showing now. That is variation. It's just like I'm talking about the US GDP for the first quarter. The US GDP for the first quarter, the data leading to that, there's going to be a variation within that. Does that make sense now? Okay, that is the variance of X. When I talk about variation within, which is the variance of X, then I also need to talk, since I'm talking about relationship, I'm also going to talk about joint variability, which is called the covariance. If there is no covariance, there is no correlation. Okay? If there's no covariance, no correlation. Now, this is the definition for correlation now. So, for covariance now. Okay? Now, because we're actually going to have a lot of variables involved, okay, then we need the idea of variance covariance matrix, because a lot of variables are involved. The diagonal, if you take a look at the diagonal of the variance covariance matrix with the variances, the variance of x1 is sigma 1 squared. The variance of x2 is sigma 2 squared. What am I trying to say here? I got q numbers of independent variables, and each of them has variance. That is what you see in the diagonal. But in the half diagonal, that will be the covariance. What is the covariance of x1 and x2? That is sigma 1, 2. What is the covariance of x1 and x3? That will be sigma 1, 3. Okay, is there, if I look at the sigma 1, 2 and sigma 2, 1, of course, they are the same, because the sigma 1, 2 is a covariant between x1 and x2, while sigma 2, 1 is a covariant between x2 and x1. They're basically going to be the same. In principal component analysis, we need variance covariance matrix. So which means you need to first construct the variance covariance matrix. But let me tell you this, how do you get the covariance that we have inside the variance covariance matrix? Because we're actually going to want to get that from data, we're basically going to use this guy. Okay, so we're going to use and in the end it's going to be, so which means, take a look at this. I'm going to take you back now. We use this to get each of the the covariance between S1 and S2, right? Now when you take a look at this guy here, this is a population variance covariance. But in statistical analysis, we don't work with the population. We take a sample size. Therefore, what we're going to end up getting is going to be sample variance covariance instead of population variance covariance. What I'm trying to tell you now, the sigma that you see here, that sigma that you see, that's a population parameter, which actually denotes variance covariance, population variance covariance. But what I'm going to be working with is going to be this guy, S, sample variance covariance. Don't forget, in a univariate statistics, where you have just one variable, we will normally talk about, there's a difference between sigma and S. Sigma is a population standard deviation. S is a sample standard deviation. So we also have the same here. Okay, I told you our destination is correlation. Okay, but there's no way I will be able to get to correlation without passing through the covariance and the standard deviation of the variable. So, which means the same way that we have a sample covariance matrix, we can also set up a correlation matrix. Okay, now we actually believe that, and of course, we're going to be using sample correlation. Okay, so the sample correlation can be written as what you see. What do you have in the middle? Oh my God, what I have in the middle. What am I using style to write? I wanted to go back to this guy. The rho ij actually equals sigma ij divided by sigma I sigma j. I want to write this in matrix. writing this in matrix, I'm basically going to have that. That is a multivariate version of correlation. Oh my God, the S that I have in the middle is going to be sample variance covariance. And the D that you see is more or less like, initially I got a sigma, right? Sigma high, sigma j. They were occupying denominator position. When they go up, okay, what happened initially before I have a sigma high? This is what I'm going to tell you. I'm going to write what I have initially, so that is going to make sense to you. This is what I have initially. If you take a look at this, what I have initially is this guy. This is what I have initially. If you now take a look at this now, if I want to rewrite this guy here, right? Do you know I'm actually going to have this guy say raised to power half. The half is the square root. And this guy here raised to power half. When this guy and this guy, when they go up, what is going to happen? This is going to be minus half and minus half. Mathematics, right? Now, that's exactly what we're doing here, like in matrix form now. Okay? Now, the principal components can be constructed by, we can construct our principal component either from the covariance matrix or from the correlation matrix. But only that I'm actually, most of the time, depending on whether the variables, they have the same scale of measurement. If they have the same scale of measurement, I'm going to use, I can use covariance matrix. But if they don't have the same scale of measurement, I will use correlation. Why am I using correlation? What is correlation? No, we got correlation by standardizing covariance. That is that. We got correlation by standardizing covariance. Okay, that's why the principal components are not scale invariants. Changing unit of the explanatory variable can change the principal component. At times when you have a different explanatory variable and they got different units. You know what I mean? So that's what I mean. Now, and I said, principal components should only be derived from sample covariant matrix when all the variables have similar scales. If they don't have similar scales, then we should use correlation matrix, because the correlation matrix in correlation we've already standardized. What is the essence of standardizing? Bringing all of them into the same level. That is the essence of standardization. Okay. And I say if one explanatory variable has a higher variability than another variable, then this variable will dominate in the first few principal components extracted from S. You remember in a random effect model, when we're talking about investigating variability, okay, we use random effect model, because random effect model is a variance component model. When you are investigating variability, a factor with the largest variance will be the one that will contribute more to the system. That's exactly what we're trying to say here. If one explanatory variable should have higher variability, okay, that will actually dominate, and we don't want that. In statistical analysis, from the beginning, we want to make sure all our variables are in the same state, like at the same level. It's just like what happened in the court of law. In the court of law, at the beginning of a case, the null hypothesis is true. What is the null hypothesis? The null hypothesis is innocent. Alternative is guilty. So an accused is presumed innocent until proven guilty. Okay, now, and this is why it is recommended to be at the safer side. If you want to construct principal component analysis, use correlation matrix to be at the safer side. Okay. That was how we said. So if you can see the last paragraph, right? So this is why it is recommended to use the correlation matrix R to construct the principal components. Okay. I need you to pay attention here. We want to go mathematical. If you don't understand, ask me question. Ask me question, and of course, I will do a very, I will answer your question. My PhD is in mathematical statistics. I understand a lot of maths and I understand a lot of statistics, but I'm not perfect. Okay, but you can trust me. Okay, now, if I want to work with principal component analysis, like I want to construct principal component analysis, what is the approach? Don't forget, we have a set of independent variables. We got a lot of them. We don't know the one to remove. Okay. We also have a response variable that we also call the dependent, but we're not interested in response for now. Okay. We basically want to focus on the explanatory variables. Now, that was why I said we consider Q X variables. Then we actually, because we want to investigate whether relationship exists among these explanatory variables, the only way to know is to actually impose a normal distribution. In statistical analysis, the most simplest form of it, for simplicity, the best distribution that we can actually call upon is normal. And that was why we said, if you look at number 2, let us assume X that you see now. Then when I say X, I'm not talking about one explanatory variable. I'm talking about all of them. They follow normal distribution. Okay, they follow normal distribution. This is what we call a multivariate normal, not univariate, because there's a lot of them. I'm going to, when you have a univariate, I'm actually going to have X follow normal with mu sigma. My f of x is 1 over square root of 2 pi sigma square exponential x minus mu over sigma all squared, where x lies between negative infinity to infinity. This guy is for univariate when I have only single x. But when I have a matrix, the matrix 1 is what you see, okay, is basically going to be mu. Then this guy here is a vector of means. This guy here is variance covariance that I showed you the other time. Okay, so if we want to study relationship among the variables, we need to apply the knowledge of probability distribution. Don't forget, we want to know the pattern. The probability distribution is about investigating pattern. Any question? Now that is step 2. Step 3, then we construct the principal component analysis. I'm trying to say, okay, the first principal component analysis is going to be Y1. It means as I have X1 to SQ, I'm also going to have Y1 to YQ. The number of principal components I'm going to construct will be the same as the number of explanatory variables I have. But in the end, I'm not going to use all the principal components. So that is the principal component. But I want you to look at the linear combination right now. Look at the A11, A12, A1Q, a constant 1, right? If you look at step 4, okay, the transpose of that is that. Okay, now, we believe the first principal component is a linear combination of that guy and X. Okay, that very guy A, the constant of A's, we're actually going to figure it out, which we're basically going to call eigenvector. Here we're going to be talking about the idea of getting the eigen, like eigenvector, eigenvalues, and stuff like that. Now, if you take a look at the approach here, this is just the mathematical approach. If I really want to do that manually, what I'm saying now is just like, okay, you know what? The first principal component is going to be Y1. The second one is going to be Y2. and I'm going to get up to YQ. But you know what? The relationship, at the end of the day, we can guarantee that any two principal component will not be correlated. And what we're giving here is a condition under which they cannot be correlated. Now, when you look at the step 10, now I told you the other time the AJ, which are the constants in the linear setup, they are the agent vector. We need to figure out the agent vector. And if I want to figure out the agent vector, okay, I need my sample covariance matrix or my correlation matrix. And let me tell you this. We're going to have agent vectors. We're going to have agent values. What do we mean by agent values? If I want to know which agent vector I'm actually going to choose, then the agent value will determine that. The agent value is the variance of the principal component. I'm going to say that again. You know, Y1, we have a variance. The new principal component, each of them, we have a variance. But I want to put it to you now. The one that we have, the largest variance is the first principal component, because the idea with the principal component is that when I convert the explanatory variables that are correlated to the uncorrelated one, okay, that will be ordered. The order of, you know, the new set of principal component that I'm actually going to have, okay, have been ordered. Ordered in the sense that the first principal component will actually have the largest contribution, followed by the second principal component, and so on like that. And how do I know? Then I will know from the value of agent value. Agent value. Agent value is the variance of each principal component. Now, if I look at the agent value, okay, then I'm actually going to choose an agent vector that corresponds to the largest agent value, the largest variance. Largest variance means largest contribution. Largest contribution actually means, oh, even though I've reduced the dimensionality in my data set, but I'm still able to retain the largest amount of information in the old variables. Okay. I'm going to, you know, I'll quickly. Now, when you take a look at what I have in question in 12 now, that is just to tell you, I'm actually going to have, if I have Q numbers of explanatory variables that are correlated, then I'm also going to have Q numbers of principal components that are uncorrelated. And each of the new principal components is a linear combination of the old ones. That's what you see in question. That's what you see in 12. And in 13, it's just like we're looking at the variance of each of the principal component that we created, okay, and the first principal component will be the one that we have the largest variance. Okay, in question 14, in 14 is adding all the variance. Adding all the variance is like, you know, you want to know the total variance.